Hi, everyone. Thank you so much for being here. Sorry about the delay. We're going to go ahead and get started with what is actually our final speaker series of the year. And really grateful for Angelos Kokkinos to come visit us today. He is a retired Associate Deputy Assistant Secretary for Clean Coal and Carbon Management in the Office of Fossil Energy. And so if you ever go into government, you can have a title like that. It takes that long to say. So something to think about. During his tenure, he was responsible for managing and planning coal research and development. He has over 40 years of experience in fossil fuels, energy generation, and air pollution control equipment design and operation. Prior to joining the Department of Energy, he was Chief Technology Officer for Babcock Power, a major supplier of steam generation and environmental control equipment for utility and industrial applications. He's the holder of 6 patents and received a BS in chemical engineering from the University of Massachusetts Lowell and MS in fuel science from Penn State University. And I'd like to say I've known Angelos probably the whole time he was at the Department of Energy. And he's going to talk to us today about critical minerals, which is an area that we're really interested here at the School of Energy Resources. We have a lot of work in this space. I've also asked him to talk about his career a little bit because he's had this really wonderful career that kind of took an interesting turn, maybe was in industry for a long time, did research, rose to a leadership position, and then ended up in the public sector at the Department of Energy, and always did it with a smile and was really someone fun to work with, even in challenging times. So Angelos, thanks so much for being here.
Thank you. Hold that until you hear what I have to say, and then hopefully I'll be able to get out alive. So anyway, it's a great pleasure being here. Holly, thank you very much for inviting me. I always enjoy talking to the younger generation because I'm a firm believer that it's the future of the country. You all are the future, and you all gonna take care of me now that I'm retired. So I need to make sure that you are taking care of me down the road. So I'm a little bit, when I went to college, I'm a little bit challenged on electronic stuff. When I went to the university, the first 3 lectures in chemistry, freshman year, were spent on teaching us how to use the slide rule. None of you probably know what the heck the slide rule is, so just so you know. Anyway, I guess I should face that. So let's start out with setting up the stage about critical minerals needs. And one thing that we need to remember is that 79% of the United States energy production is based on fossil fuels. About 80% of that energy needs in the world are based on fossil fuels. So almost everything that we touch has some form of fossil fuel association with it. Anything from drugs to food to clothing, infrastructure, and of course, power generation. However, the energy landscape is changing permanently. And we see it in power generation, what coal production, power from coal has been half of what it has been 10, 15 years ago. And that renewables are starting to contribute a significant part in the power generation sector and will continue to play a significant role in the power generation sector and in other energy needs that we have. So for an old fossil like myself, renewables are here to stay, and it's something that contributes to our economy and can contribute to our economy in the future. One major issue that renewables have is their intermittency. They are dependent on weather effects. And as a result of that, and that is a major issue with that. And as a result of that, when we talk about renewables, we have to also talk about energy storage. And there's energy storage in various forms. For example, what I've been taught when I was, and what I have seen, the traditional energy storage for power, for example, is what it's called pump storage. You take water, when you make electricity that is not used, and you pump it up a hill, you put it in an artificial lake, and then you pump it down, you draw it down when the power need is great during the daytime, for example, whereas at night there isn't that much. Or, for example, you make compressed air, put it in the ground, and then you draw compressed air up when you need the power. So a lot of focus on storage has been on batteries. And there's a lot of critical minerals that are associated with batteries. So let me show you what I mean by intermittency. And these are some examples on intermittency. The one that I want to focus is this one. This is February, starting on February 6th, I believe, in Texas. And you all heard about what happened in Texas last February. There were significant outages. And what is also happened there was, as a result of those outages, there was close to 180 or 190 billion with a B damage to the economy, including approximately 200 deaths associated with the loss of power. So there was a significant economic and human event. What is also interesting in Texas is that Texas has the highest capacity, generating capacity of renewable power other than California in the country. Texas at its peak requires about 76 gigawatts of electricity. About 30 gigawatts of wind power is installed in the state of Texas. So here's what happened on the midnight of February 8th. Wind power, which is green, was producing about 22 gigawatts of electricity at that time. And within 12 hours, this is the mid-morning of February 9th, it was less than 1 gigawatt. For a couple of reasons. The wind died down. And what happened at that time is because there was no storage available, gas in blue picked up, and coal in black picked up. Coal went up to 85% or more of its capacity, which is more than almost full load. And this variation in load needs to be addressed and accounted for when we have an electrical system like we have. Electricity is the only product that it has to be consumed immediately. We expect to have electricity when we flip the switch. And what I want to tell you is on this is that this is not just a 1-in-100-year event. Exactly the same thing happened in Texas in 2011, and it happened in 1989. So it kind of reproduced itself every 10 years. It also happened in Texas on the summer of 2018. Again, you see how wind dropped off. But it doesn't happen in Texas. It happened in the Southwest, which is, I believe, Wyoming may be part of the Southwest Power Pool. Maybe not. But Southwest Power Pool goes from North Dakota all the way down to Louisiana. And then you can see here at a very cold day, the wind production dropped and it got picked up by fossil fuels. And you want to look at Germany? Here's Germany. A couple of events in 2019. So this is why we need to have, if we're going to have renewables, we would need to have some sort of storage and some sort of power that provides backup. So the next slide, oh, I'm impressed. It's got a thing here. The next slide says that fossil fuels do provide reliability, and in this case, we'll be providing reliability to the renewable energy, where renewable energy provides the main supply, and then fossil fuels allow for the grid to move up and down. But they also provide critical feedstocks, and they also provide for energy storage. Our economy and our standard of living has increased dramatically since fossil fuels came to our life. The standard, for example, life expectancy in 1900 was 48 years. Today, 78. But there are problems. There's no free lunch. And the problems are that they do produce byproducts that are not good for us as a human species. So we need to be addressed. And we have addressed them. Just the two pictures that I want to show you. This is Los Angeles in the late 1960s. The brown fog, smog. This is Los Angeles this year. Big difference. And we address those through technology. And we can address the issue of CO2 emissions from fossil fuels through technology. And you all doing a great job in addressing it through carbon capture, utilization, and storage. And we've done it in the past, and we can do it in the future in this area. So let me talk a little bit about batteries and how this, because it is one of this energy storage options that we have. Specifically, how batteries can help us address this intermittency, but also to look at the materials that are required in the batteries. So the favorite battery that everybody's using is lithium-ion battery. And this is the typical composition of a 100 kilowatt hour battery in an electric car that you have, like a Tesla or a Volt or Nissan. My son has one of those Leaf, I think they're called. So typically they weigh about 1,100 pounds, about half a ton. And lithium is about 30, 40 pounds, cobalt about 30 to 60 pounds, although Tesla claims that their batteries to have significantly less than that, 10 to 15 pounds. Nickel, graphite, copper, and manganese. All of these, with the exception of copper, are in the list of the 35 critical minerals that the Department of Energy has shown that are important to our economy. I'll talk about two of those today. And the two that I would like to talk about is cobalt and graphite. And you probably know a lot more about batteries than I do, but they're basically lithium-ion battery are very popular and very good because they are high energy density, they have no memory effect, and they have a low discharge rate. So let's look at, I did some back of the envelope calculations on the transportation sector because people talk about batteries for cars and trucks. And if you're looking at the North American car and truck sales in 2019, we sold about 17 million cars. In 20, because of COVID, we were down to 13.5 million. The current North America car sales are about 250,000 cars, a small fraction of the car market. The total US production is about 450,000 cars in 2020. Just to give you an idea, China produced 1.2 billion in 2018. So let's take one of the ingredients, cobalt. The worldwide use of cobalt is 140,000 tons of pure cobalt or oxides in 2020. It's one of the key ingredients, and of that production, the United States gets about, imports about a third of it, 50,000. Its uses are very interesting. It's used to, every jet engine that we fly on contains cobalt in it because it's used for high temperature alloys. It's used in batteries, catalytic systems, catalysts, and also for hard materials, cutting materials or protection in cutting materials. So one of the interesting things that happened is that batteries back in 2005 represent about 23% of the market. Now they're up to 50% of the market, or even more than that. And the interesting thing about it is that cobalt, 2/3 of the world's resources currently used are located in the Democratic Republic of Congo, of which it's not known for its democratic ideas, of which 3/4 of that, of those assets, of those resources, are owned by the People's Republic of China, are owned by China. In the Democratic Republic of Congo, they are estimating that about 40,000 children are used to mine the cobalt. And in 2019, there was actually a lawsuit that has been brought up in federal court in DC against Dell, Tesla, Apple, Microsoft, and Google by paying Congo children that they in cobalt mines. However, we need cobalt. So the amounts that we're going to need if we are going to go to significant production, for example, of electric vehicles are enormous. There are a lot of different predictions as to how many electric vehicles we're gonna have. The International Energy Agency predicts about 670,000 electric vehicles produced a year by the year 2050. McKinsey company, which is a consulting firm, says that about 30 million we have to be produced by 2030 if we are to meet the Paris Agreement goals and things like that in transportation. Needless to say, if you get some of these numbers, and if I made a back calculation of about 15 pounds of cobalt per electric vehicle, you're looking at approximately 200,000 tons of cobalt per year, if not more like, or up to 4.5 million tons of cobalt between now and 2050, just to address the transportation sector. Keep in mind that the entire reserves of the world are about 7 million tons. So Houston, we do have a problem. So what are we going to do? Because demand is going to be difficult. We are going to be having renewable energy. We are going to be building electric vehicles as we should. And we're going to need to have batteries to power those electric vehicles or to back up the power that we need. If you're going to look at natural ore, it would require massive quantities of processing of what I call dirt. The typical concentrations of cobalt in ore range between 0.6 to 1.1% concentration of cobalt into the ore. So you're looking at massive amounts of ore. The U.S. has, according to the USGS, about a billion tons of cobalt containing ore as a resource, but it's not classified as recoverable. The recoverable portion of it, I believe, is about 70,000 tons total. So we need to get that cobalt out. Opening a mine in the United States takes a long time, 10+ years. So we need to find other sources of cobalt. And this is where you all come in. Look at mining abandoned mines and waste from those abandoned mines. Looking at coal mine and steel production waste. We had a project in Pennsylvania where we find some almost commercial grade waste of cobalt in it. And in mines or from copper, nickel, and iron mining, byproducts and processing. Acid mine drainage is another area that is very, especially from coal fields, 600 to 1,400 parts per million of of cobalt and former sites that process nickel for and pyrite concentrate products. So what opportunities are there for the University of Wyoming? You were all very successful in getting awarded from the Department of Energy a program called 4CM, Carbon, Rare Earths, and Critical Minerals Program. So some of the things that you could do is investigate the levels of critical minerals that are in legacy mining in Wyoming. See if they contain things like cobalt there. Testing for those levels, develop separation processes that are lower cost and most importantly, minimize or do zero damage to the environment. So you don't create another problem for your kids to take care of it. Develop partnerships with other institutions and state agency and private industry. Develop substitutes for these batteries. And last but not least, recycling processes. When we look at graphite, another interesting material. Graphite is carbon, and you all have boatload of carbon in Wyoming. I think the whole state is supported by underground by carbon. Natural graphite is not produced in the United States. 70% of its production is located in China. And large deposits are being developed in Africa. Synthetic graphite, which is being made, is made by processing at the high temperature amorphous carbon, such as petroleum coke with synthetic organics. And then it's put into its crystalline form. And I'm going back to my undergraduate senior thesis project. You can make it out of acetylene. The Tesla Gigafactory, which could provide batteries for up to 500,000 EVs, would be requiring about 93,000 tons per year of flake, of feedstock, of graphite, which is over 100% of the current level. So it would require basically 6 new graphite mines. And that's, of course, assumed there is no demand from Europe or Asia for that material. By the way, Volkswagen announced, the biggest car maker, announced big plans for EVs. Ford announced a $2 billion, I think, investment in Tennessee on electric vehicle production. Another area that nobody appreciates is the electrodes for electric arc furnaces and aluminum production. You need to make aluminum and you need to make steel, especially since most of the steel now is recycled. You need cathodes and anodes, electrodes that are made out of part of it, out of carbon and graphite. The graphite market is expected to go from 16 billion to 26 billion over the next 5 years. The typical cost of an electric arc furnace. These are the big furnaces that they use to melt steel. By the way, the US production of steel is about 78 billion tons per year, 2/3 of which is produced by electric arc furnaces. They consume $25 to $30, require $25 to $30 per short ton of steel in Houston in cost for these electrodes. The current price is $170 to $250. These things are huge. The increases are a lot of increases, mainly because we use a lot of more recycling of steel scrap. The petcoke prices have increased because that is the primary feedstock, and of course the dependence on crude oil pricing. So what can you do with graphite? Again, I'm going to go back to 4CM carbon ore. You have a lot of carbon around in the state. But also, as I understand, you guys are already working on it with microwave. So there's areas that you can have a role in it. You can go into gasification with acetylene, graphite, and CO2 capture. Cost, challenges are the cost. It has to be competitive, quality, consistency, and last but not least, consistency of the product. And last but not least, how do you get it from your little laboratory environment to where you are producing tens of thousands of tons of that stuff in an effective, costly, in a cost-effective manner that can compete with others? I think that's the last slide, and I was pretty good at it. So I'll be glad to answer questions. Be kind to me because I forget things sometimes. Yes, sir.
Speaking of recycling, has there been any efforts as recycling used or expended batteries?
Yes. Yes, there has been. The question is speaking of recycling. Yes, there have been. And there is a significant amount of research that has been going on with support from the Department of Energy in the area of recycling, especially of batteries. And that is it has to be recycling, it has to be in the mix. I mean, we can't just take all these batteries and just throw them in the garbage. It has to be in the mix. The issue that you have with recycling is that you have the demand is increasing faster than the feedstock that you have to recycle. I don't know if I make myself clear. So recycling will not be able to address the supply issue that I have with some of those critical minerals. So that is the issue, but recycling is in the mix, yes. Yes, Steve.
On your slides, you talked about feedstocks from the Democratic Republic of Congo,
Yes.
going to China. On that slide, wasn't it also talking about Taiwan supplying their feedstock?
Yes, the major suppliers of batteries to us is Taiwan, South Korea, and China.
Do you think that that's part of the political and military issues of China wanting to bring Taiwan back into the fold?
I don't know. I think it has to do, part of it is, I'm kind of a student of history. I love to read history, and most of the wars, including the Trojan War, were fought for economic reasons, and I'm sure economics have to do with it. By the way, for those of you that don't know, the Trojan War was fought because the Trojans applied fees to copper. Copper was the primary equipment of choice at the time, and all the copper mines were up in Black Sea. So all the ships that were going through, the Trojans were stopping it and putting in extra fees, and the Greeks didn't like that, so they found an excuse to start the war. So little bit. Yes, sir.
So
I'm sorry. Go ahead.
Well, I've got a question then maybe a follow-up. You mentioned about electric arc furnaces. I wondered if you have any comments on the future of metallurgical coal, both in the US and overseas.
That is a very good point. The United States has excellent supply of metallurgical coal, and I don't want to get into politics here, but this issue of not wanting to have coal mining could spill over to metallurgical coal. It has two things that metallurgical coal does for the country. One is it's a very good export income because its price is about twice, if not 2.5 times, the price of steam coal. The second thing is that it's a strategic material, since most of the production of metal, of steel is overseas. So we have some sort of a control of strategic resources. So if to me, and this is my personal opinion, to me, putting it and making it difficult for people to mine coal, it could impact the production of metallurgical coal, which is mostly from the eastern part of the country, and that creates.
Yes, I mean, you mentioned the word control. My follow-up relates to air pollution controls for deep mines, which a lot of metallurgical coal is, if you think about it globally. Do you think the coal industry has the appetite for investment in better, let's say, control of mine emissions of methane? Let's forget about thermal coal, let's forget about CO2 related to carbon issues and power reduction.
Based on recent discussion that I had with a couple of the coal producing mining companies, yes, they are. They understand that. The issue that they have is as with any industry and every private entity is basically the costs that are associated with it and how that impacts their product. But when you look at methane emissions and the overall emissions, the statistic that I saw, there were about 28 million tons of methane being emitted, I think, in the country, totally. And coal, as I recall, and coal mining operations and stuff, is only about 1.5 million, maybe 2 million tons, or some
Yeah,
number
I mean,
like that.
my quick response to that is emission inventories, the oil and gas industry has learned recently could be falling. If you we're thinking about top down, bottom up, there's some wiggle room there for the whole industry, let's say, to potentially put itself in a stronger rather than a weaker position.
Right.
So I won't say any more. Maybe offline we can talk about that.
Yeah.
But at the UN level, I know that's a big issue in terms
But
of
it's something that the coal industry needs to address.
because any uncertainty associated with, let's say, thermal coal mines, you've got the same issues with respect to the
Correct.
ventilation systems and how
Correct.
arcane many of them are.
Correct. And you have other associated issues, not just methane, with coal mining. That the
Thank
black
you.
lab
I'm just
is-
pleased to hear that you think there's an appetite for it.
Very good in Australia before.
You were trying to
Yeah,
ask.
some.
Is there any prediction for the resources on mineable graphite? Like, can they, if they want, can they just extend production, or do they come to a limit that would make a drastic price increase? That would make synthetic graphite making
Yeah,
easier, because the higher the price, the
I looked at trying to find numbers on natural graphite in the United States, and unfortunately, the major source is the U.S. Geological Survey, and I couldn't find any numbers on that. On it, so I really don't know.
But in the rest of the world, like if you told us we'll need more graphite. So like in Africa, can they just build more mines? Or are there limits in mineable resources that would expect that a drastic price increase for the graphite?
I don't know. I think our effort, my preference would be that we try to work on synthetic graphite and enhance our position in synthetic graphite, the production of synthetic graphite. One more.
It looks like there's actually a question in the Q&A on the webinar.
Oh, yes.
Oh, I'm sorry. I'm sorry. I'm sorry.
I'm gonna repeat them all.
No, start over.
Sorry about that.
Okay, anything else? Angelos, any last words for the folks in the room?
All right, you asked me to talk about my career lessons learned. And I put in the slide up and after this, but I want to tell you something, those of you that are students. I was not an A student, and I'm serious about this. I was not a B student. I was a C student. So, but what I did was I tried hard and worked hard and listened to people. And as a result of that, knock on wood, I had a fairly decent career. By the way, about my title, I forgot to tell you is that the longer federal jobs, the longer the title is, or the more words that it has, the less important it is. But thank you, Harley, for that anyway. So, let me. Oh, do I push the down
Oh, no,
button?
it's because I touched my question.
Okay, so here's some of the things that I learned over the years. The most important one is to listen and learn from others, especially people with experience. One of the things that I learned is that 70% for what you do, if you're an engineer, is based on engineering equations. 30% is based on what mistake did I make on the last project. Okay. So always look at that. And I'll give you an example. The first project that I was given when I was a freshman engineer I was given, this was back in the oil embargo days and the energy crisis in the 70s. Steam boilers, I was a burner engineer, and I came out of Penn State with great credentials as a combustion expert and burner expert. So I was given the task of designing a burner that eventually became the standard product of the company, but it would operate at as low load operation as possible with stable flame without having support oil to help it keep it ignited. So I went to this power plant and we were testing it, and I wanted to test it. So I told the operator to set one row of burners in to see how it would, the system, the other burners would react to this upset of load. And he said to me, what do you want me to do it? You want to do it manually or automatic? The operator, I said to the operator, I want to do it automatic. So to my surprise, I shut the whole 400 megawatt boiler down. Tried again another hour later. Same question from the operator. Same results. I knew everything, right? I was the bonus baby out of Penn State, you know. Third time around, I asked him to do it. The operator says to me, you know what? I don't do it that way. Says I put it on manual first, and then by hand I adjust the feed rate of the fuel, because in an automatic system, and the good dean is an electrical engineer, can tell you, you have a sinusoidal curve that the automatic system ought to compensate, so that it results in an unstable flame. Sure enough, we did it his way, and it worked. And the rest is history. I got good marks from my boss saying, oh, you succeeded. So that's what I mean by talking to people and listening and absorbing what they have to know. Know your limits and don't be proud. Ask for help. Tell people, hey, I don't know this. Or tell your boss, I'm out of my comfort zone. He may tell you, hey, you're the only person that I have to do this. But at least you alert people. At the end of every project that you do a lesson learned exercise. Find out what worked and what did not work. Very, very important. Be flexible and be patient. I have a lot of young engineers that came to me and said, oh, in 2 years, I want to be a vice president. Yeah, you can. Some of us are boy or girl wonders, but you have to be patient, because time, especially in this field, is associated with experience, is associated with knowledge, and that's how you come up on the top of the pyramid. Keep an open mind, and most importantly, think outside the box. That is extremely, extremely important. those English courses that you have to take, they're there for a reason. Trust me. I hated them, especially since, I don't know if you people realize that I'm not from the United States. Okay? That's just, you know, this is not a New England accent that you're hearing. My wife is pretty good. You know, they don't have the letter R in their vocabulary, by the way. They're New Englanders. So communicate, but also in terms of communication, do it in simple terms. This is what I found. This is one of the things that, because of my limits in English language, I had to use simple terms when I communicate. I did not use a lot of, my wife being an elementary school teacher, did not use to a lot of SAT level words. Very important to be ethical, especially in the engineering profession. You don't appreciate, and I worked for many years with high pressure vessels and equipment, steam boilers. You had to follow the ASME pressure code. You couldn't get permitted by the state. And I always told people, nor did I want. I said, the last thing that I want is to go and tell somebody how I did something that hurt their loved one. Tell it like it is, but do it nicely. Okay. And the best part is have fun and enjoy yourself. The moment you wake up in the morning and say, oh man, I don't want to do this job. Oh, you know, what a drag. It's time for you to do something else. Thank you.
Thank you, guys. Thanks so much to everyone for being here. Really appreciate it. We don't see you. Have great holidays. This concludes our speaker series. And just so you know, I think these are true for any professional, especially those of you that are going to work on developing relationships in your career. So thank you all. Take care. Welcome. Bye.